Yeah, in the historical moment when Lagrange died, so he stopped writing papers, and the Lagrangian ideas needed to be developed. And this is when Piola has more or less your age. So the idea of Piola is the following. If we have learned to study the equilibrium of a being using a principle of minimum, can we find a way for studying the equilibrium of deformable bodies? Three-dimensional deformable bodies using a principle of minimum. So, if you remember, Euler is taking a curve, is constructing the section which remains not deformed. Okay? Then he is assuming that this section remains orthogonal to the mean curve. So this is a very peculiar, very particular body and a very particular way of deforming. Okay? The only thing which can happen is that one section and the closed section can have a relative displacement. But each section remains not deformed. Okay? So this was very clever. Because technology managed to advance a lot using this theory. However, we want to study more. We want to understand other ways of deforming of bodies. Okay? So we want different shapes, and we do not want to accept any particular assumption about deformation. This very bad situation when a section remains not deformed must be avoided. Okay? Remark this. If you write Euler equation, this is an ordinary differential equation because we have only one variable with respect to which you are calculating derivatives, which is the abscissa in the reference configuration. Okay? So you have a particular set of equations which are very simple. We talk about one-dimensional continuum. You have a body which is a continuum, but it has only one dimension. A being is a one-dimensional continuum. Okay? We go back to our data now. So you have a body which is in 3D. You have the placement key. You have its shape, actual shape. Okay? You have externally applied load. And we want to know which is the shape of your body under these applied loads. But this body is three-dimensional. So you have that the reference shape is constituted by a set of material particles for characterizing each of which you need three coordinates. Okay? So you need x1, x2, and x. To let you understand how people were behaving in other epochs different from this one, the professor of Viola, his name was Vincenzo Bonacci, came to him and said, now you generalize Lagrange theory. He was 22 years old. So, you write the deformation energy, you write the functional, and you look for the minimum. And he spent 28 years of his life doing this job. He died being 50 years old. Okay? So, we will not use the procedure of Viola because we are exploiting Lagrange tensor calculus. So, K is a map defined in the reference configuration going in the actual configuration. So, this symbol means you have a point in the reference configuration and you have an image in the actual configuration. Okay? In coordinates, this is x1 equal x1 of capital X, x2 equal a function of capital X, and x3 equal another function of capital X. Okay? We have written f ai, which is this one. I is 1, 2, 3. A is 1, 2, 3. These are the coordinates in the Lagrangian configuration. This is the coordinate in the actual configuration. Okay? So in every point here, you have a matrix, and this matrix takes a vector V, capital V, and it maps in another vector, small v. Okay? So this F allows you to know what is happening to the epsilon cube of your body. So we already spoke about this. Okay? And we have introduced G, which is F transpose F, which is the deformation measure, minus 1, 1, which is the deformation measure we are considering. Okay? Okay. Now, we have a problem. Considered a lot how to tell you this. So I hope that you have an experience about oil and fluids. The fluids for which you define a pressure and a density. Okay? In a fluid, in equilibrium, you can evolve only an externally applied force, which is orthogonal to the boundary of the container of the fluid. I try to tell you this slowly. If you have a container, and if you have a fluid inside, here, on the boundary of this container, the fluid is exerting a pressure on the container, which is a force Pn, where n is the normal. One other fluid is only pushing the container. There is no shear force. So there is no force in this direction. Okay. Again, I'm following nearly word by word the presentation of Piola of this problem. What is another fluid? Another fluid is a fluid for which the deformation energy is given as an integral of W of rho, the actual density of the fluid. The deformation depends only on the mass density. If you assume this, you get as a result that the force exerted by the fluid on the container is only a pressure and you have no shear. We will see this in detail. I will give you written notes with all the deduction. So you will be able to reconstruct all technical details. Okay? But now I want to give you this idea. What you can apply on a continuum depends on how this continuum is made. If you have a fluid, if you have ever seen a fluid climb and stand horizontal, you can take a solid, you clamp it on one side, it stays horizontal. You cannot have a fluid, you clamp from one side and it stays horizontal. In equilibrium, of course, you can have a jet, but you have another phenomenon, you have kinetic energy. Okay? Or if you take a cord like this, it can be only vertical. You will never be able to keep it this way. Okay? So the possibility, why? Because this animal is not capable to exert shear. This is only capable to exert traction. It is not able to exert compression. To respond to compression. Okay? So, what became immediately clear to Piola was the following. Given a body, this body cannot respond to every external action. You understand this? If I have a body, the poor body cannot do everything. It can do something. No, this statement is so trivial that that's clear. No? You cannot demand to something everything. Okay. So a given body, more specifically, a given body cannot exert any response to external actions. The typical example, which you should have seen already, which is rather familiar, are fluids. Fluids can exert pressures, but they cannot exert shear forces. This is not true, so we can say more precisely, in equilibrium, if capillarity phenomena can be neglected. I mean, some conditions, fluids cannot exert shear forces. Okay? So the idea, which is clear in the mind of Piona, and the reason for which, in my opinion, is one of the main mechanicians in the history of science, is the following. He understood that you must start studying deformation energy. You consider deformation energy as a starting point of your theory. Then you go ahead, you study properties of a given deformation energy, and you characterize the kind of actions which your body can sustain. Okay? So I will not write the problem of minimum of energy. We will formulate this problem later. What we do now is we calculate the first variation of deformation energy. So it is a good idea, probably, that Tomek asked me to do a whole presentation before. So try to understand the strategy we are considering. I have shown you a particular case, the equilibrium of a beam. I gave you the whole presentation, starting from the energy. I said, I want the minimum of energy. I calculate the first variation of the energy. This energy was made of two terms, deformation energy, external energy. Okay? We equated the first variation of external energy plus first variation of internal energy, deformation energy, equals 0. And we wrote the equilibrium equation. So, what we say? Integral of Km over 2 second squared. This is internal energy. Then we wrote external energy. Okay? Then we wrote total energy. Then we said, we want the minimum of total energy. We calculated the first variation of the total energy, and this is equal to the first variation of internal energy plus the first variation of external energy. We equated this to 0, and we found this equation plus boundary conditions. Okay? This was the scheme. Okay? Now, following the other, we want to repeat this scheme in the case of three-dimensional deformable continua. Okay? Now, what I can do? We start to study this first variation. Why? Because this animal plus this animal has to be 0. If this animal is made in a given way, you cannot add to it everything for getting 0. So, we study the first variation of energy, to understand which kind of external forces can be applied to that body. Okay? I will repeat to you this many times, showing you examples. Okay? But I want to give you a general vision of the problem. So, I repeat, if you are a fluid, the energy depends only on density, and as a consequence, the external forces applied to the fluid cannot have shear. The poor fluid is not able to resist to shear. So here, if you apply an external force, an external energy with a shear component, here you have no shear, and this equality cannot be verified. So you don't have equilibrium. Okay? But we will see this in detail. Okay. So this is the motivation for which I start writing the deformation energy only, and I start calculating the first variation of deformation energy without writing the total energy of the system. Look, it is very easy if you understand this mathematics reality. So, the deformation energy is equal to this equation, where W is the density of deformation energy in every point. You accepted yesterday the fact that I have one section, the other section, they move one with respect to the other, and you have a deformation energy related to the infinitesimal element of beam. In particular, we wrote that the energy depends on phi prime. You remember? So you have a beam, you cut it in small pieces, usually they call it beam element, and we associate it to every small beam element a given energy. Now you have the potato, you cut it into small cubes, every cube is deformed with F, and you have a function which tells you the energy associated to that F. You sum up all these energies, epsilon tends to 0, and you get this. Okay? If you have doubts about this, we can talk. Okay? You know why I suspect that you may have doubts? Because Viola wrote 25 pages for justifying this formula. So clearly, in the mind of people, this is not obvious. I became accustomed. I forgot when I was not sure that this is true. Okay? So, you can reconstruct this integral in terms of Riemann sums. So you would write this sum over I of the energy Wi of Fi, where I is one of these cubes. You sum over all cubes, Then you ask to the size of this cube to go to 0, and you get the 0. Okay? So this is a possible energy for your system. Now I need to find the first variation of deformation. So I can write integral over C star WF plus delta F minus integral over C star of WF. In this way, it is obvious. Now we need to start using some technical things. Why? Because F is a matrix. So it is 3 times 3 matrix, if you have chosen a basis. So you get 9 real variables. So actually, you have to write this way, considering each variable. Okay? Look, we decided to be careful and to say everything slowly. So I open here a mathematical parenthesis. If you have a function of n variables, f, x1, x2, xn, this is equal, the Taylor expansion of this function is given by f x10, x20, xn0 plus df over dx1 calculated in x0. This means all these numbers times x1 minus x10 plus df over dx2 x0 times x2 minus x20 plus plus df over dxn in x0 xn minus xn0. Okay? And then you have plus infinitesimals. Okay? Consider that already here we are much better than Piola's book, because in Piola x1 is A, x2 is B, and x3 is C. So formula become very quickly a nightmare. We instead are very clever, because remember, what is this? This is the f over the x1, the f over the x2, the f over the xn. So you can write this sum over I of df over dxi times xi minus xi0, and you forget all this. And you have written exactly the same thing. Right? And this is also handy for a computer. You send a command for, Now, what we have here? We have W, which is a function of Fi(A). So you have a function of 9 variables, the 9 components of the matrix F. I can apply this equation, this Taylor expansion. As this is the first variation, I can forget higher order terms. So this I forget. Okay, so this is equal to integral over C star of dW over dF AI delta F in A. Summation over repeated indices. Okay? Tonight I try to take the books of Piola on my computer, and tomorrow I will show you the 5-page long equations which he writes, not having the right formalism. Okay? There are students, PhD students, who periodically come to me to see that I am too abstract, too general, and these indices are useless. But do the calculations without indices if you are able. This is the answer here to give them. Without Levi-Civita tensor calculus, we cannot do anything. Period. It is impossible to study the theory of the phenomenology. This is not an extreme position, this is a practical position. Do you know what this is? Do we want to write this equation explicitly? Then I have to write 2 more lines. If you are clever, because you could write F1, 3, you could be so stupid to write it dk1 over dx3. But you could be even more stupid. You could write this dx over dc. And you could be so stupid that for you F2 is dy over db, quickly losing all regularity in your formulas. Regularity is a sign of order. And you have to be able to discover the order wherever it is. This quick formula is not magic. It means something. You know, you learn what it means, and you are happy. You go on ahead without trouble. Okay? Let's go ahead. Delta epsilon definition equal integral over C star of dW over dF delta Now, there is a problem. What is the variation of the derivative? We claim that the variation of the derivative is the derivative of the variation. Okay? Lagrange wrote many pages for this, discussing this point. In these pages, you don't find an answer. The answer you will have only when we study the theory of Sobolev spaces. I tell you, you learn by heart, and one day you will understand. In the Sobolev space H1, you can take delta and place it inside. Of course, you cannot do it always. In a very precise set of functions, which is a Sobolev space H1, this you can do. Okay? But if Lagrange was happy about the statement that the derivative and the variation can commute, you can be happy for a moment. Okay? You know, students become very precise when they want to stop. I don't understand this, so I don't study it anymore. Okay? So we invert the derivative and the variation. By the way, we did it already with electrons when we calculated the first variation of the energy in Euler B. So we already accepted it. So this is equal to the integral of dw over dFi derivative of delta Okay, now Leibniz rule holds also for partial derivatives. By the way, I want to also let you understand that people are not becoming clever by chance. You must be born in the right place, in the right moment. Piola put to these calculations for a reason. You will put me like a name. Why? Because Napoleon had conquered Italy. I explain you why. Napoleon conquered Italy. He became king of Italy in Milan. And he decided that Italy was a nation. So he called a professor from Pisa, Vincenzo Manci, and said, "You write a book in mathematical analysis in Italian." He wrote 8 volumes. These volumes now are considered in Italy too difficult. So the mathematical analysis which engineers were learning in 1801 in Italy is considered now too complicated. Okay? Piola knew the theory of integration by parts of many variable functions and could apply the calculations we are doing now because as a student he had learned this. Okay, should I tell you what l'époque des Lumières was? I don't know how to say in English, Illuminism. Okay? There was a moment in which to be a mathematician was not a shame. Napoleon pretended to prove a theorem in the French Academy because he wanted to tell to people that the emperor considered so much mathematics that he tried to prove a theorem. Okay? We do this calculation. You know, this is a trick, so you cannot complain because I told you that a student could do this in 1802, so you feel bad if you refuse to do this. Okay? This is a rhetoric trick. So, you have this high summation of this. If you do this derivative, you have a free index A. So this is a vector, a Lagrange vector. What happens if you calculate d over dx at A sum over A? You are calculating the divergence of this vector. Okay? You apply Leibniz rule. So you get d over dxa, dw over dfia delta qi plus dw over dfi d over dxa delta qi. This is Leibniz rule. The derivative of the product is the sum of this plus that. Okay? This is a little bit more complicated from a technical point of view, but this is exactly what we did yesterday. You agree? Okay, try to be good actors. Try to have a smiling face telling me understand. If not, consider that this is a number. Ki is a real function of 3 real variables. Okay, so all these functions have the same nature as u. The only difference is that u is a function only of s, while all these functions are function of x1, x2, x3. So I need to write d of partial derivative with respect to xa. Okay? So, this is the divergence. The divergence of all these elements. This is the divergence of only this element here times delta qi. And this is exactly what we have in the first relation of it. Okay? Believe me, Navier and Poisson tried to simplify this presentation. I can reach for you the result in 1 hour, and you will understand perfectly it if you repeat it 2 or 3 times. And the story is saying, if you try to simplify this, you can only make a mess, a total mess. Okay? So, I suggest you strongly to understand this theory in this way. Okay? There is also another advantage. This theory can be generalized very easily. While in the way in which Lagrange formulated this theory, generalizations become very difficult. Okay, so take and memorize the formulas we have written there. I am replacing. So this is exactly what we did before in a slightly more complex formalism. So delta is deformation equal integral over C star of dw over df dI. By the way, this is a tensor. Somebody calls it Piola-Kirchhoff tensor. If you want to quarrel with me, you add Kirchhoff. Okay? This is Piola tensor. Okay? Kirchhoff has done nothing. So, this anymore times d over dx a delta ki is equal to integral over C star of d over dx a dw df delta ki minus integral over C star of d over dxa dw over df delta ki. This is the standard trick we are applying in this context. Now, I hope that you know Gauss theorem. The integral on a volume of the divergence of a vector is what? Is the integral of the flux of the vector on the boundary of the domain. Remember, integral of div of something, of a vector field, on a domain V is equal to integral on the boundary of V dot n. This is Gauss. Okay? So, I can take away this divergence. I can add here boundary, and I have a free index A and A. This is the normal is orthogonal to the boundary of simple star. So, for the difficulty of this presentation is purely technical. What you need to know? Divergence. You need to know Taylor expansion for functions of several variables. We wrote it before. Then you need to know Leibniz rule for derivatives. Okay. And now you need to know Gauss theorem. So maybe I repeat better this Gauss theorem. You seem to be a little bit oriented. if I have system and I have integral on system of the divergence of something. Okay? So you have here a vector. Which vector I have? dw over dFIA delta Qi. This, there is a sum. So this is a vector. You have only one free index. Okay? So you have a vector field here, V, and you have the divergence of this vector field. So you have integral of the divergence. Okay? Divergence theorem tells you that if you are on the boundary of C star, you have a normal n. The integral of the divergence is equal to the integral on the boundary of C of this animal dot n. Okay? If you have studied some fluid dynamics or some electromagnetism, you must have seen Gauss theorem. Okay? So what we are doing? We are, instead of calculating the divergence of solid and then the integral over the volume, we consider the flux of this vector field through the boundary of the domain. So, Gauss theorem is very useful because it allows you to transform a volume integral into a surface or vice versa. Okay? So if you think, we can try to look for it, but in the book, in both books, we gave you this theorem. Okay?
Różnica wcale Państwu dałem, to się nazywa differential operators. Tam, jeśli chcecie, żebyście to
Okay? Now, let us look what we got. We got that the first direction of extent of deformation energy is equal to the integral on the surface of something. I can change the order. Times delta Ti and integral in the volume of solid times delta Ki. We have done nothing. We have integrated like that. This is a logical truth. You cannot do anything. This has deep consequences. We must discuss carefully. So, if you have a deformation energy which depends on F, you integrate by parts. And after integration of the parts, you get that the first variation of deformation energy is equal to integral of volume something times delta Ki, integral on the surface of something times delta Ki. For the moment, for you, this is a simple calculation, but I want to show you slowly which are the physical consequences of this. Okay. What is the variation of energy? It is an energy. What is delta Ki? It is a displacement. Which quantity multiplied at displacement gives you an energy? You call it force. So, the external load has to exert on your body some actions. This action will be represented by a potential. Okay? So let us move this blackboard at the top and let us reason about what we have to do. We will need to write an expression for external energy. We do not know yet. Okay? We'll have an external energy. This external energy plus deformation energy will give you the total energy. The equilibrium will be this equation, delta total energy equal delta external energy plus delta deformation energy. Okay? We have calculated the deformation energy, the delta of deformation energy. What is this delta of deformation energy? It is up. This animal has to be equal to 0. Okay? Now, imagine that you are stupid, stubborn, blind, very stupid. So, you take your body and you apply to it a force per unit time. So, on the boundary of this body, you apply a force per unit time. You say that external energy is equal integral over a curve gamma, which is included on the boundary of system of F linear delta Ki. So this is the inner product of radius. Okay. You are ready to listen. You have a kind of gravitational force applied on the mind. You have the inner product of the force times the velocity. Yesterday you said that you are ready to accept it. Okay? I calculate the first variation of these, and you get obviously this. It is linear. Okay? Then you add delta deformation. Delta deformation is what? it is integral over the boundary of C of pure tensor times delta K plus integral on the volume system of divergence of pure tensor delta K Pn. P applied to the normal. P applied to the normal delta K. Divergence of P delta K. Okay? D has to be equal to 0 for every delta K. Okay? You believe that this is possible, easy. You believe that your bodies are all bodies. All bodies are described by the deformation energy you have introduced. Okay? Can I choose a delta K which is concentrated on your curve gamma and 0 everywhere? Exactly as we have done yesterday. You can do it. This is 0. This is 0. And very clever. Very clever. Very clever. What you discover? That F lim is 0. So, you wake up one morning and you say, there are no forces that you will try. External world cannot exert forces per unit. I mean, this is very similar to those who were against covariance. The model of people, the model of the universe of the people who were against covariance was a model. A theory. In their theory, the Earth had to be in the center. So they refused to see everything. They didn't want to see everything. Their lenses were deforming reality, and they could see only the Earth in the center of the universe. Here, the problem is less dramatic. Nobody is being burned because he believes the contrary. However, we have a terrible logical contradiction. You cannot claim that the external world cannot exert force per unit line. You simply must say that bodies whose deformation energy depends only on F cannot sustain forces per unit line. There is something dramatic on this. Somebody is worried by the fact that fluids cannot sustain shear forces. Nobody is worried about this. They are teaching you Euler fluids every day. Nobody says that this is strange. You have to understand carefully. We are talking about models, not about phenomena. Euler fluids is a model. This model is a cannot consider externally applied forces exerting shear. Okay? Yeah. This one. Imagine to have here a curve gamma and you have a force per unit line applied on this curve. You have studied Ampere law in Maxwell equations. You have a force per unit line. Okay? Which is written, the potential or force per unit line is written integral of the force in a power placement. It's like the gravitational force. You have the force times the displacement in a current. So only the projection of the displacement along the direction of the gravitational force is important. Okay? So this is exactly the same thing. Okay? So, I repeat, if you have on this curve a delta t like this, concentrated on this line, all these integrals are 0, and you are led to the tragic consequence that there are no force per unit line. Okay, now the problem is, how do we interpret this? This is the problem. What is the meaning of this result? Which is true. Now, Piola in 1850 concludes the model of continuous body in which you have deformation energy depending only on F is a theory with some limits. These kind of bodies cannot sustain forces per unit line. So you have fluids which cannot sustain shear forces, and you have first gradient materials which cannot sustain forces per unit line. What can sustain, which are the external actions applicable to first gradient materials? Look at this equation. Forces per unit area, forces per unit volume. So to a first gradient material, you can apply forces per unit area, tractions, or compression forces or shear forces, forces per unit area, because this is a force per unit area, because this n times a displacement integral over a surface is equal to an energy. Or forces per unit volume. So when you write the potential of externally applied forces, you are prisoner of your assumption. You can only write integral of bx times delta t on the volume plus integral on the boundary of C of fx delta. This is the only thing you can do. If you consider only these forces, this plus this equals 0. This is the Euler equation of equilibrium. Remark, it is written in the reference configuration, not in the Abelian configuration. You have seen the version of this equation maybe in the Abelian configuration. Okay? And then we have P n plus fx equal 0. Which tells you that the force applied per unit surface to your body is equal to the Euler stress separated with the normal n. If you try to apply other forces, you get a paradox. There are no other possible external actions applicable to continuous flow of first kind. Okay? Unfortunately, Euler dies writing that I will study in the next paper what happens if the deformation energy depends on the gradient of F. This story is interrupted until in 1960, so 110 years after, Midland continues the work of him. Midland, Tubin, Rivlin, Green, Atkin, so people from different countries. In Russia, Serov. In Poland, Sokolowski.
I think also the request also.
I'm not right. Brinowski wrote something.
Brinowski works on the request.
Yeah. You should give me the references.
Sadov wrote a popular book about the science. Very nice.
Yeah, but the book for students was written by Sadov. He starts directly from L-gradient materials. Okay, so what they are teaching you is a bad resume of the final results obtained in terms of variational fluids. I try to explain you how. They wake up one morning and they say that there is a tensor. It is not pure tensor. They consider Cauchy tensor in the Euclidean configuration. And this magic tensor is used for expressing forces per unit area. So what they do, in order to avoid integration by parts, so in order to avoid the calculations, we needed less than 1 hour. Okay. Let us assume that we need to follow a course in mathematics to learn divergence theorem, partial derivatives, Taylor expansion. Say 6 months of study. I mean, divergence theorem is not useful only for this. You cannot live without knowing divergence theorem. I mean, you cannot be an engineer without knowing divergence theorem. I cannot live without knowing divergence theorem. With the simple integration by parts and imposing the postulate of the minimum of energy, you get as a result that you have a tensor P, and that the equilibrium is given by this volume equation and this surface equation. Moreover, you immediately have a strong message. If you have energies per unit volume, and these energies depend only on F, you cannot expect the capability of your continuum to sustain forces per unit line, or forces concentrated on one point. So if you have forces per unit line, or forces concentrated in one point, you must change your theory. I am very happy that I had very good professors of philosophy. You know why? Because after the day when the professor of mathematics came to us and proved that square root of 2 is not irrational, 1 hour after, the professor of philosophy came and gave us a talk about Pythagoreans. Follow my reasoning. Imagine that for you only rational numbers exist. For you, number is equal to rational numbers. Then somebody comes out with a theorem and he proves that square root of 2 is not a rational number. So what you say? Rational 2 is not existing. You arrive to say that this side of the triangle is not existing. You have two possibilities. Either you change your theory or you stop admitting that something real is real. Pythagoreans decided that this triangle is not existing and that square root of 2 is not existing. The Jesuits, who were against Galileo, didn't accept that there are some spots in the sun. They said the telescope of Galileo was broken. People in this room attacked me violently, telling that there are no edge forces. So they are so intrinsically full of the theory of first gradient, they are so badly twisted by one theory, only one theory, that they refuse to see what is outside their theory. In my opinion, they taught me the theory of first gradient, and for a long while I believed that there is nothing else outside. I discovered these things when I went to France. I was already 30 years old, so my brain had been already frozen by age. But I was able to learn something new. Why? Because of my professors in philosophy and mathematics. They had prepared my brain to distinguish between theory and reality. The theory of Cauchy continua, theory of first gradient continua, is a particular. You can invent another, more general. We have to call it Piola continua. The theory of Piola continua. So you use the theory of Cauchy until you can use it. It's very effective. You can apply it in many situations. However, if you have forces per unit line, you cannot use it anymore. Simple. So you are young enough to learn this. Okay? Okay, let's talk a little bit. Lagrange integration. Okay? So I want to explain you this because it is very useful for the application. If you have a fluid or a solid which is occupying in different instants different positions, okay, you can decide to write your equations here in the actual configuration. Which is the problem? The actual configuration is changed. So it is unknown the domain of your fields. Think about it. If you have a beam, and this beam is vibrating, so it is moving up and down. Okay? And you are like people teaching you divergence of Cauchy stress plus external forces equals 0 here. You can try to apply this. But you do not know where the equation is defined. Okay? So you have a terrible problem. You have a moving boundary and a moving region, and you have a set of equations defined in a region which is unknown. So, you are crazy. You become crazy quickly. If you are like you are, you write the equations here. If you write the equation in the reference configuration, the domain is always the same. So if you write div dw over df plus b equals 0, and dw over df and equal externally applied forces. Of course, the forces are applied here, but you can use the pullback Viola transformation for writing your externally applied forces on the reference configuration. Then you have everything defined in a domain which is not moving under your legs. No, you stay stable in a given domain. Now, the genesis of that paper I will give you is the following. Some fluid mechanicians discovered that it is much more clever to have a Lagrangian description and follow the material particles of a fluid in their flow, having labeled them in the reference configuration. So they wanted the equations of capillary fluids, which are fluids, particular fluids, we can decide if we want to study them, in which the energy depends on rho and gravity. Okay, these are very important for surface tension phenomena and the incidents. So they told me, can you write for me the equations in this domain? Because in this way our code works better. You know, I was naive and I said, yes, I will find it. And I will give you the lecture about it. After 10 hours of lectures, I arrived at the point. So I looked for the equations and I could not find them. So I phoned to my friend Victor Eremeyev, who is the typical Russian school, the Soviet school of fluid mechanics, and we spent a week doing calculations. And we found the version of equations which are put here for capillary fluid. And I gave the talk to my student. And I published the paper. So that paper is lecture notes for students at PhD level. And not result about, it's not revolutionary, but it is a useful result about capillary fluid. Then I had the opportunity to teach for 1 year analytical mechanics for students in physics, and you know, physicists are very good. So at the master level, I gave them these lecture notes, and they studied them, and they understood. So I think that you can do it, you can read it, even if you are not at the PhD level, all of you. Okay. Now, I want to use this hour for comments and comparison. Okay? To deduce the equations here, mathematically speaking, is rather easy. Because You do the calculations we have done this morning and you get this equation. But you know, the problem of Viola is that he was alone against the whole French school who didn't believe to variational principles, which is very strange because Lagrange was professor in Paris, but he died. No, Lagrange was very clever. He was 16 years old and he married a very young girl, beautiful, rich, and belonging to a very powerful family. And the witness of his marriage was the king of France. Then they cut the head of the king and he became revolutionary. Then Napoleon got power and he became a supporter of Napoleon. When he thought he was becoming too old and he could die, he prepared his last glory. With his wife's family, he organized the burial in Pantheon. Very important men in France are buried in Pantheon. And he managed to manipulate to become one of the first scientists to be buried in Pantheon. So it was very. However, he didn't manage to leave behind him a strong variational school. While Viola wanted to do it. So, I'm telling you the historical framework for explaining you why Viola attacked this problem. If I have the equations here, how can I transform the equations here? So he wanted to transport the equations from one configuration, the reference, to the actual configuration. So he has an equation of the kind d of p plus sum equals 0, and he wants to see how these equations are transformed. Okay, this is not easy. I have written in the lecture notes, so if you are interested, you can check it. But it is not easy. I don't advise you to study it now. You need to start a PhD. It is technically difficult. You need some time for digesting it. While what we have done this morning is rapid, easy, and you can understand it with some efforts. Because you need concepts from differential geometry. What is astonishing is that Viola, for political reasons, he wrote the equations here. People said, equations here are not good. We need equations here. So in order to prove that his theory was good, he painfully transformed the equations in the Lagrange configuration. But for doing this, he started the modern differential geometry. So he started the school of Italian differential geometry, which has as names Beltrami, Bianchi, Levicini. So modern differential geometry was born for continuum mechanics. So I don't believe that you know very much about differential geometry. It is a modern theory used in many mechanical applications, and it was the tool used by Einstein to formulate general relativity. So another thing. understand it. Viola had a principle minimum of energy. He wanted to formulate the theory of deformable body respecting his ideology. You know, this is ideology. Okay? He formulated the principle of minimum of energy and he wrote the equations in the reference of equation. Then people in France, Poisson, Navier, started attacking him, saying, "You are a mathematician. Your mathematics is useless. We are true mechanicians and we write everything in the actual configuration." So in order to prove that these results were really good and useful, the book was obliged to write everything in the Eulerian configuration. Tomorrow we will see that this is absolutely useless if we want to solve with numerical tools the problem of deformation of force. The equations of Viola are very good already. You don't need to do anything anymore. Okay? But for historical reasons, Viola was obliged to transform these equations into the Eulerian form. And painfully, look, I wrote these divergences with capital letters because I wanted to mean that you have the partial derivatives with respect to capital X. Okay? If you write the equations here, then you need to use the partial derivatives with respect to small x. The coordinates in the Eulerian. So, divergence has to be written small d. Okay, now, in the books of Viola, 1848, you discover, with many calculations, that he is able to write d of a tensor t plus a transformation of the b, so it is another b, equals b. So he proves that passing from Eulerian configuration and Lagrange configuration to Eulerian configuration, the structure of the equation is the same. And he manages to write Cauchy stress tensor in terms of Viola stress. He did it for political reasons. He knew that this was useless. He wanted to write it for pushing his results in the French and he wrote it in Italian. So French is okay. Something written in Italian is not existing. So they ignore it. See, the Italian school developed differential geometry. Now, if you type Viola transformation in the web, you find several 100,000 documents. But for the wrong reason, because this is the basic tool of differential geometry. Mathematicians are using this transformation for their theories in differential geometry. They are changing charts in a manifold. So they prove that this equation is invariant under change of coordinates. Now, the story is continuing this way. In standard courses, they start with this equation. They start telling you this is true. Why? For physical reasons. Okay? They don't want to explain you all the variational principle, all the calculations. They treat you as stupid. And they give you the final result. Okay? Which is offensive. I believe this is an insult to the intelligence of you. Okay? Then, consider how crazy stuff. For many years, the only way for solving practical problems was to manipulate this equation. So they manipulated this equation in a way or another. Okay? And in engineering sciences, the flow of a fluid in a pipe or Semmelmann solution for the deformation of a cylinder, all these analytical solutions calculated by hands were obtained starting from this equation. But one morning, von Neumann invented calculators. So he invented the technique of finite elements. It allowed the application of finite elements, which we started to discuss this one. So, somebody understood that he needed to write the equation in the reference configuration. It was much better. But this somebody was lazy. Instead of opening the books and finding where Lagrange configuration was studied, they postulated this equation. They transformed it back to the reference configuration and started studying it. So, as they need the minimum of energy for applying the method of finite elements, what they do? They postulate the final result of P. They put back the equations in the reference configuration. They integrate by parts, but starting from the result and coming back to the energy. They painfully rediscover energy and then they apply finite elements. I mean, I think this is a proof of mental disorder. This is the strength of habits. When you are accustomed to reason in a given way, usually you have not the force to change your mind. If you read the good books, Maitri, Sadov, Tolkien, you find the correct way of reasoning. You start from the minimum of energy or some weaker version of it, okay, and write your equations in the reference configuration. And then you attack the problem of discovering in an approximate way the solutions, so maybe you use finite element. Okay, this morning, so we are commenting, okay? You are tired, we did a lot of calculations. morning I told you that for the theory of the being, you need 4 derivatives if you want to write these strong equations of a union. Okay? So you need a regularity which is much higher. Okay? For strong equations. Now look here. To write this equation, you need only f. F is the first derivative of ki. Okay? So, for writing energy, you need C1 functions. Functions one time differential. If you integrate by parts, you have another derivative here. So you have one derivative. This is a function of f. So at the end you have the derivative of f. So the second derivative of k. Okay? By the way, in a particular case of W, the equation I wrote there are called Beltrami-Mitchell equations. The equations of equilibrium, a strong form of equation. So, if you integrate by parts, you must have more regular fields. So people are calling div b plus b equals 0 strong equations for equilibrium. Why this one? So delta epsilon f plus delta epsilon x equals 0 for every delta chi. These are called weak equations for equilibrium. So you can characterize equilibrium with the weak equation. Sometimes your equilibrium conditions can be found using the strong counterpart. So at the end, now, in this moment, in this historical moment, our calculation tool is a phenomenal machine. With the phenomenal machines, we write codes with finite elements and we directly use the minimum of energy. Period. I could not teach you anything. Anything else. I give you the energy and you look for the minimum. So you could tell me why you wanted to integrate by parts. Because I wanted to tell you that the boundary conditions can be only forces per unit line, per unit surface. So when you write the energy total now, you have the potential energy plus the potential energy of forces per unit volume plus the potential energies of the force per unit surface. Otherwise, your model is not self-consistent. So this integration by parts is useful if you want to understand which are the correct boundary conditions to be given. But they are not a tool for finding the solution. Not anymore. Okay? Then we have another comment. This maybe I can give you as an exercise, so you can try to practice tensor calculus. We said that W is a function of G, because G is the deformation. Okay, so you must impose that the deformation energy depends only on G. So our W of F is equal to W bar of G of F. Okay? You find this in the paper I told you. So somebody among you could not immediately recognize, if you take another book, my Viola tensor with the other people Viola tensor. Actually, they are the same, because I'm writing it in terms of the good variables F. If you want to write in terms of G, so if you have double bar of G, then dW over dF is equal to dW bar over dG times dG over dF. If you manage to write this equation, you will recognize standard Viola stress. They are the same. They are written in terms of another deformation energy. Okay? This is very useful, and it is an important exercise to write it. Okay. Now, another comment. I'm sure that somebody told you, miracle, force per unit surface depends linearly on the normal. They call it Cauchy postulate. Okay? And it is very elegant what Viola, tomorrow I will try to reduce some words of what Viola wrote about this. He said, miracle, divergence theorem. Which miracle? It is not a miracle. You integrate by parts, you get the divergence of something. You apply the divergence theorem, you get that the force per unit area depends linearly on the norm. What you want? There is nothing safe. It cannot be differently. Okay? Okay. Now, before going to having lunch and unfortunately, if you have a second grade, this story becomes much more difficult. This is the true reason for which we needed to wait mid before having the development of geometry. You know, in 2012, I published with Pierre Seppecher and Angela Amadeo a paper which was a part of Angela's PhD thesis and a lot of work from myself and Pierre Seppecher. We wrote the equations for nth gradient of mathematics. I had not read Viola's book before. I knew about it, but I remember. When I opened the book, I had literally a heart attack because 40% became more and more worried because I said, finally, could I find something original or everything is already written here? You know what? When I read the last page, I found that the good Viola did not manage to find the actions on the boundary. So, he could integrate by parts one time, and he got this. Plus, some terms he called omega. He says this omega is 0 if the material is first present material. It is not 0 if the material is second or higher gradient. And I have read some papers studying this omega for the next application. I knew that he died before. I mean, that was a posthumous book, so he could have not written it. So I was very happy because my paper is talking about this omega. Okay? Now I tell you the story. You integrate by parts. I will show you for second grade, but you must digest it for the first grade first. Okay? Then we try to attack second grade integration. You know what you get? You get forces per unit area. This. You get forces per unit line. You get forces concentrated on edges, wedges, so points. But you also get double triangle forces, K forces. What are these forces? Are angles like this. So what you have? You have delta K, the normal derivative of delta K on the surface, and you have an angle whose inner product with this normal derivative gives you an energy. So think about it. If I have a displacement, the dual energy of a displacement is a force. If I don't have a displacement, but I have a derivative along a direction of a displacement, the dual of this angle, how can I call it? Migrin calls it double forces. So we need to understand what means this type. Okay, so you have understood the thing. If I have the second derivative of delta K along the normal, this is a triangle force. If I have the K normal derivative, I have a K force. What is the physical meaning of this? We will discuss in some cases. But mathematically speaking, you understand. You integrate by parts and you get what you get. You cannot discuss. You get a result. And you must interpret this result. Okay, so for concluding, Viola wrote with words in this omega I have this derivative. And he said this could be very interesting for many applications, and he also talks vaguely about this application. In this moment, it is very popular to talk about metamaterials, materials having a strange beauty. They are pure. No, mathematics gives you a tool for imagining what will happen much before it happens.